It's 7:05. We'll split the difference. All right, everybody. I'm Edwin Olson. I'm happy to see so many people here. This is great. I'm a robotics a faculty member here in CSE. I primarily work on robotics, and one of the problems that we have in my graduate level robotics class, 568, is that we use a lot of linear algebra. So many years ago, we had linear algebra reviews as part of the class itself, which meant that it was actually about 7 lectures into the course before we ever uttered the word robot, because we had about three classes of linear algebra review and 3 classes of probability review and an overview. It was awful. So what we've decided to do is to do these sort of remedial review sessions. Now, the inspiration for these courses comes a little bit out of my personal experience taking linear algebra myself. I took a linear algebra course, and I worked very hard at it, and I got a good grade. But at the end of it, I could multiply matrices, I could compute SVDs, I could do Gaussian elimination, but I found that I couldn't actually bring those skills to bear on new problems very well. I didn't have the intuition that I needed in order to be able to apply those techniques to new problems, at least not the way that I really wanted to. So the goal of this course is to basically assume that you guys have a similar problem, and to basically go back over some basics of linear algebra, assuming that you pretty much have the mechanics down. How many of you have actually taken a linear algebra course? Great, great. So most of you. But the goal here is to go back over that material again and to reattach intuition to it. You know, the first time you took it, you were probably so busy just trying to remember what to do that despite the fact that the professor doubtless said the words that I'm about to say, the intuition just isn't the first thing to settle in. So we're going to go back and try to brush up on that sort of thing. Let's see. So the course is organized into 3 sessions. Today is going to be geometry. So we're going to look a lot at column spaces and row spaces and null spaces. Also thinking about how these relate to the intersections of hyperplanes. What is a line? How do we get points out of these things? We'll talk a little bit about rank, but we'll mostly save the discussion of solving linear systems until next time, which is Monday. Same time, same place, just on Monday. The focus of Monday is solving linear systems, so AX equals B. We'll review LU decomposition, Cholesky decomposition, talk a lot more about rank and the importance of it and what to do when your matrices have insufficient rank, or what to do if you have an overdetermined system. Along the way, we'll hit some applications, so we'll cover regression on Monday, among other things. The third lecture is Friday, so a week from tomorrow. And that one is basically looking at the spectral properties of matrices. So we'll look at singular value decomposition, we'll look at eigenvectors, we'll look at principal component analysis, which if you're taking a machine learning course might be useful there. We'll probably talk a little bit about the power method, a little bit about random walks on graphs. All these things come out of that sort of thing. There was something else I was going to say, but I can't remember what it is. Any questions about where we're going? Great. So I encourage you to come to all 3. Hopefully you'll be able to pick up lots of new and cool stuff. So let's start with some basics. The basic is that I'm a very short person. All right, I'm going to grab my notes, otherwise I'm going to forget what I'm supposed to be doing. OK, so we're going to start off with the idea of a vector. Hopefully this is very straightforward. So a vector, we're going to typically write as a column of numbers like this. What does a vector represent? What types of things can a vector represent? Yeah, it can represent the coordinates of some point. So here's an x-axis and a y-axis. We can call this x and y. So we could have this point. What else could a vector represent? Direction? Yeah, let's call it a direction. Yep, or sort of a motion. Right? If you started off at 0 and moved in the vector 2, 1, you'd end up at the point 2, 1. That's all very great. Of course, we can manipulate vectors. We can add and subtract them. If I had 2, 1 plus 4, 3, we just do element-wise addition, and everything's very happy. What sort of restrictions do we have if we're adding vectors? What sort of properties do those two vectors need to have in common? They need to have the same dimensions, right? We're talking about a fully defined point in some dimensional space, let's say a 6-dimensional space. I don't know what it means to add a 6-dimensional point to a 3-dimensional point. So we're going to assume that we're always adding vectors of the same length. Hopefully nobody's lost. Great. All right, so one of the simplest things in linear algebra actually turns out to be one of the most important, the idea of a dot product. So let's use these two vectors that we did before to save myself a little writing. If I wanted to compute the dot product of these two vectors, what would I do? Anybody? Right, so I'm going to multiply, do the element-wise multiplication, and then add the individual bits. So 2 times 4 plus 1 times 3 is 8, is 11. Interesting thing to remember about a dot product is that the result is a scalar, always. Right? It's not a vector anymore. We do a dot product, we end up with a scalar. All right, now what does a dot product mean? Right, we can do the math, right? That's what we just did. What sort of geometric intuition can we have about dot products? So here's our happy vector 2, 1. Here's 4, 3. That looks like 4, 3, right? What does the dot product of those two actually mean? Right, right. So basically what we're going to do is we're going to take, I picked some bad examples here. Let's actually let's make up a different vector just because those are so coincident that it's hard to draw. Let's pretend that I had ended up with this vector, whatever the heck that is. So what we're going to do is we're going to take one of the vectors and we're going to project it onto the other one, which basically means something like this. Right? And so what should this angle here be? This should be 90 degrees, right? So the dot product of this vector, call it A, and this vector B is almost this length, whatever this length is, but not quite. So one way we can remember that this isn't right is that the dot product of A and B should be equal to the dot product of B and A. It shouldn't really matter which way we do it in, right? So if we did try that experiment, if I projected B onto A, right about here, maybe, right, this length is a different length than this length. Right? So basically what we didn't do is we didn't take into account the length of the second vector. Right? If we multiply this length here, which is just the straight projection, onto the direction B, and then multiply by the length B, we're going to end up with the dot product. All right, so to say it again, a dot product is basically a measure of how close two vectors point in the same direction. Anybody remember the trigonometric equation that is associated with dot products? Right, so the magnitude of A times the magnitude of B times the cosine theta. Right, so this is the length of vector A, the length of vector B, times the angle times the cosine of the angle that separates them. All right, so this is pretty cool, right? Because if they're pointing in the same direction, theta is 0. So cosine of theta is going to be 1, and we're going to end up with a big dot product. If they're pointing 45 degrees, the dot product keeps getting smaller and smaller. What happens when theta is pi over 2? Right, the vectors are perpendicular, and one doesn't cast a shadow on the other. Right, so at that point, the dot product for two perpendicular vectors is 0. This was page 1 over here. All right, so one joke that I give, how many of you watched the videos from last year? Great, so I can reuse the same jokes. It's not really a joke so much as my wife makes fun of me because I use sort of technical jargon in everyday life. I don't know if you ever do this. I'll say something like, I'm going to the grocery store, so I might as well swing by and pick up the pet food because they have a large dot product with each other. Right? So you could say something like, my thesis and my final project in the class have a high, you want them to have a large dot product. Right? Intuitively, you want them to be pointing in the same direction so that doing work on one is like doing work on the other. Right? What's the worst possible case? So they could be perpendicular, right? In which case, your final project in the course is on skinning potatoes, and your thesis is on, help me out, something not having to do with potatoes. Robots. There we go. Robotic potato peelers. That would work. All right. Then all of a sudden, woo! I guess actually the worst case would be if the dot product was negative. I guess that means that your final project might be to get someone to go in and delete your thesis. I don't know. OK, great. So let's do a little checkpoint. What is the dot product of x with itself? So it's 1 only if something is true about x. Right? If the length of x is 1, then the dot product of x with itself is also 1. What if x is not a unit vector? Right, it's the square of the length of x. Good. There's another way you've all taken a linear algebra class. What's a different way for me to write a dot product that doesn't involve the little c dot? Yes, x transpose x. Right, so those of you who aren't a little dusty with transpose, the one mistake that I see most often when people are doing transposes is that they think of it as rotating the matrix, which is wrong, right? What is a transpose? What are you actually supposed to do? Right, make all the rows columns and make all the columns rows, right? So it's not rotate the matrix, it's exchange the rows and columns, right? Especially when you're looking at vectors, they look like the same operation. Don't make that mistake in your class, you'll feel stupid. I'd feel silly. OK, let's see. So we already talked about perpendicularity. This is another important concept. And perpendicularity builds on dot products. So A and B are perpendicular if what is true? Right, A transpose B is 0. Right, that means that they're perpendicular. So let's try a little exercise. Let's suppose I've got my happy vector 2, 1, and I want to make a vector that is perpendicular to it. How would I do that? Or just cutting to the chase, who can tell me a vector that is perpendicular to 2, 1? You're close. I heard someone else say it again. -1, 2. Right? So 2, 1 transpose -1, 2. Right? You can see what's going to happen. We've got the same sign, the same magnitudes flipped around. So we're always going to be multiplying a big number by a little number. So we're going to end up with the same magnitude for both of the multiplications. And because we flipped the sign of one of them, one of the products is going to have the opposite sign of the first product. Everybody, that makes sense to everybody? Right, so we're going to end up with 0. That's great. Is that the only vector that's perpendicular to 2, 1? No, in fact, we could throw in a lambda here. Right? For any old scalar lambda, those two are still going to have a dot product of 0. All right, so there are an infinite number of perpendicular vectors to 2, 1, but they all have this interesting property that they all live on a line. Right? They're all multiples of 2, 1, or multiples of -1, 2. Great. Let's try this in 3D. So let's suppose we have the vector 3, 1, 6. Can someone tell me a vector that is perpendicular to that? -1, -2. I need to put. It's great. I have a very bad demultiplexer. So someone over here was saying something. -2, 0, 1. Yeah, that works. Good. We can actually use the same trick as we did before, too. Basically, we could just say, let's make one of these a 0, and then swap and flip the signs. So one thing we could do is we could say, let's make the bottom one 0, and then just find the perpendicular vector to these guys. Right? So this would be -1, 3. Everybody check in your head that that works? right? I can actually do this by zeroing out any one of these guys and flipping the other two. So I can make the first one 0 and flip these two around and make one negative. So that's going to be 6 minus 1. Yeah. What's the next one? 0. Flip these guys around, make one negative. Great. So what we're finding is that there's a lot of vectors here. Now the question is, in the previous case, all of the perpendicular vectors were on the same line. They are all multiples of each other. Are these all multiples of each other? Say it again. Same thing. What do you mean? Same. Right. So you're actually ahead of me. But empirically, what we want to see is that these are not all multiples of one of them. Right? We can't just pick one. For example, this is not a multiple of this guy. But if we take two of these guys, we should be able to construct any of the other ones as some linear combination of these guys. And what we'd find is that no matter how many of these that we came up with, if we pick two of these guys, such that they weren't degenerate, blah, blah, blah. We're going to skip a lot of asterisks in this lecture. We would be able to find some scale factors to construct any of the other ones. So let's do that just for giggles. Boy, I almost picked a bad one. Let's pick these two and construct this one. So can you give me a lambda 1 and a lambda 2 such that this times this plus this times this equals this? Well, what does lambda 2 got to be? Lambda 2's got to be 3, right? Otherwise, there's no way to get the minus 3 over here. And actually, this one's got to be minus 6. So I didn't even do the math on the rest. But yeah, that's going to work out. All right, so this is what we'd find, that in 3 space, if we consider some vector, and we consider all of the other vectors that are perpendicular to it, they're going to live in some 2-dimensional subspace on a plane. Everybody on board with that? What do you suppose happens in n-dimensional space? I have a perpendicular vector. I have a vector. In what's true of all the vectors that are perpendicular to it? They all live in some n-1 dimensional space. Right? If I took the right set of n-1 of them, I would be able to compute any other one of them as some linear combination of those n-1 basis vectors. All right. How are we doing? Thumbs? All right, and pace? Too fast, too slow? Let's do just right. We need 3 bits. If you're happy, put a thumbs up. All right, things are going to keep building on top, so it's important that we have a good basis for where we're starting. All right, so here's page 2. All right, so let's consider some of the properties of these guys. Let's consider we're in two-dimensional space. We've got some vector. As we said before, what we're going to end up with is a set of vectors that are perpendicular to this vector, and they're going to live on what? On a line, right? We're in two-dimensional space. The set of all vectors that are perpendicular to this guy are going to live on some line, right? We can see this vector and this vector are all here. These are different values of that lambda. In two-dimensional space, I might draw that something like this. Right, so here is some vector, and all of the other vectors that are perpendicular to it live somewhere in this space. All right, so what do these two constructs have in common? Is there a term that we can apply to both of them? Say it again. You caught me asking a hopelessly ambiguous question. That's right, but it's just not the answer I'm looking for. So these are both hyperplanes, right? The set of vectors that are perpendicular to this vector, this is a hyperplane. This is a hyperplane. As we go up into higher and higher dimensions, you give me some vector, the set of vectors that are perpendicular to that live in some hyperplane. So in general, if I have an n-dimensional space and I give you a vector, the set of perpendicular vectors forms an n minus 1 dimensional subspace, which we call a hyperplane. Right? So here's the key thing. If I start off with an n-dimensional space and I start handing you vectors, you can think in your head that each one of these vectors corresponds to some hyperplane. Right? Every vector has a hyperplane. And as I keep adding hyperplanes, I'm dropping the number of degrees of freedom I have down. Let me explain that a little more carefully. So here we are in three-dimensional space. I give you a vector. Here's the set of vectors that are perpendicular to it. What happens if I give you another vector? We test my artistic skills. That's what's happening. All right, so let's try this vector. This vector also implies a set of other vectors that are perpendicular to it, and they're going to live in a plane as well, right? And so that might look something like that. Is this at all legible, or is this marker too dead? A little bit of both. I won't use it long. That'll be my solution. All right, now if I took this hyperplane and I said, what vectors are perpendicular to both this vector and this vector? Right, so we're going to be looking at the intersection of those hyperplanes. Right? If I have an n minus 1 dimensional hyperplane and I compute the intersection of it with another n minus 1 dimensional hyperplane, what size subspace do I end up with? N minus 2. In fact, we can see that happening here. If I take a plane and I intersect it with another plane, what do I end up with? A line. Right, so I'm going to end up with a line that looks something like this. Right, this is the set. On this line lie all of the vectors that are perpendicular simultaneously to this vector and this vector. All right. So here's the basic idea. We can start collecting vectors. Remember, each vector corresponds to a hyperplane. And every time we add a new vector, we're reducing the number of degrees of freedom that we have left. We started off in three-dimensional space. You give me a vector, that gives me a hyperplane. I'm down to a two-dimensional space. You hand me another vector, that gives me another plane. I intersect it, I'm down to a one-dimensional space. What happens if you give me 3 unit vectors and their corresponding hyperplanes in 3 space? I end up with a point. It's a zero-dimensional space. OK. I keep scrambling my notes, which is a really bad strategy. OK, so a little more terminology. There are special words associated with the case when we're in an n-dimensional subspace, and we've added n minus 1 hyperplanes. And again, an asterisk applies to all these things. We're assuming non-degenerate hyperplanes. In other words, the hyperplanes aren't linear combinations of each other. So for the most part, we're just assuming that everything's nice and linearly independent for today. So what do we call it when we started off with an n-dimensional space, and we've added n minus 1 hyperplanes? Well, how many degrees of freedom do we have left? 1, right? And there's a special word for a one-dimensional subspace. It's a line. All right, what do we call it when we're down to 0? We already did this one. It's a point. Right? So there is a potential source of confusion that comes up quite a lot. It's in 2 space. So we can describe a line. So a line has 1 degree of freedom. Right? It's as though we took an n-dimensional subspace and added in n minus 1 hyperplanes that had to intersect. How much wiggle room does a hyperplane have? N minus 1 degrees of freedom. So a line has 1 degree of freedom. A hyperplane has n minus 1 degrees of freedom. Now, if n equals 2, we're living in the plane, what happens? A line and a hyperplane look like the same thing. Right, so this is a place where I think a lot of students go wrong in building their mental intuition. Because ordinarily, a good problem-solving strategy is if someone tells you a difficult high-dimensionality problem, you say, well, let me try solving this in 2D first. But in 2D, we have this problem that you're drawn into thinking, you're drawn into confusing potentially lines and hyperplanes. Right? And so if you generalize incorrectly from 2D to higher dimensions, you might get something wrong. So let me ask this question. If I have a line in 2 space, how might I represent it? What's the general equation for a line in 2 dimensions? Y equals mx plus b. That's partial credit answer. I'll let that go. Let's go with ax plus by equals c. Right? Why don't I like y equals mx plus b? Yeah, so what about a line that goes straight up? Right, so y equals mx plus b has a singularity in it, which is really inconvenient if you're dealing with, let's say, a physical system that could very well be pointing north. Right, so we like the more general form. All right, so in 2 dimensions, we can describe a line like this. OK, quick question. How do we describe a line in 3D? A little louder? ax plus by plus cz equals d. So I said that I asked for a line in 3D, but it's Michael, right? Yeah. What did Michael actually give me? The equation for a hyperplane in 3D, right? How many, this actually this only narrows down 1 degree of freedom in 3 space. There is a 2-dimensional subspace that is the solution to this. Right? So this is where a lot of students go wrong. They're thinking, oh, a line in 2D is just I can write it like this, like a single equation. Therefore, a line in 3D must look like this. No, no, no. This is the equation for a hyperplane in 2D, which happens to look like a line because we're in a 2-dimensional space. This is the equation for a hyperplane in 3D. Right? So very, very oftentimes people get that wrong. All right, now there's something interesting about the way that I wrote this. What does this kind of look like in terms of the stuff that we've already talked about? I've got ax plus by plus cz. What does that look like to you? It looks like a dot product, doesn't it? All right, so let's have a dot product, a, b, c, with x, y, z equals d. Right? ax plus by plus cz equals d. So what is this saying about how dot products relate to hyperplanes? Well, we define a hyperplane in terms of a vector, and every point that lies within that hyperplane has a specific dot product with that unit vector. So that's not clear right now. Let's draw a picture. We're going to try this in 2D. And let's consider this unit normal. All right, and we already know that all of the points that are perpendicular to this, they form a hyperplane, which of course in 2D is just a line. Right? In this case, let's consider this guy. Now, what do we know about every point on this plane, on this hyperplane? So if we consider some vector from the origin to this point, what do we know about it? Right, it has no magnitude at all in the normal direction. Right, that's what we've been saying, right? That if I consider the vector from 0 to p, it's going to be perpendicular to n. Let's call this n hat. So in other words, I can write this equation as n transpose x equals 0. Right? That's a way for me to write the equation for a hyperplane that goes through the origin. Right? That's what I have over here. I have n times a point in question, and if d is 0, then what I know is that this describes a hyperplane where every point if you consider any point on that hyperplane, the vector from 0 to that point is perpendicular to the unit vector, to the vector ABC. All right, so I stumbled over that a couple times. I'm going to try saying it again and make it really clear because it's really important. This dot product corresponds to a hyperplane. Every point in that hyperplane satisfies the property that the vector from 0 to that point has no motion in the direction of the unit normal. Right? In other words, the dot product from 0 to p is the vector from 0 to p. Take the dot product with n, and you're going to get 0. Everybody with me? It's not the most lucid explanation of my life. Yes?
Is P the XYZ vector or ABC vector?
Is P is the XYZ vector. Yeah. And this is n. Now I lost my train of thought. What if we don't want the hyperplane to go through the origin? There's a lot of hyperplanes out there, not all of them go through the origin. How do we shift this hyperplane to go somewhere else? Yeah, we're going to change the right-hand side. Right, so let's actually draw that. So let's keep the same n. Nothing wrong with our normal vector, but let's try to come up with the plane with this hyperplane. Right? Everybody agree that that's still a perfectly good hyperplane. It just doesn't go through the origin. What we want to do now is use the same sort of intuition. If I consider any point on this line and the vector from 0 to p, what relationship do I want it to have with the normal vector n? It has the same dot product. Right, so let's actually consider that right here. What is the dot product of this vector onto this? Let's assume for simplicity that this is a unit vector. What do? I take this vector and I project it onto this line. Right? And so what is the magnitude of that unit vector? What is the magnitude of that dot product? It's this distance, which is, well, C or D, depending on which one we're doing. What I'm going to switch to a notation now, which is n transpose x equals b. So let's erase some of the letters that I haven't been consistent with. All right. So let's call this b. Everybody on board? Right, actually, b is chosen because of y equals mx plus b. It kind of feels like the same sort of offset. Right? We're not doing any changing the slope at all. We're just kind of changing where that line appears. All right, let's try some other point on this hyperplane. Here's a vector from here to here. What is the dot product of this vector onto the n hat direction? It's also b, right? Let's pick a point that's not on the hyperplane. Just make sure, right? Let's pick this point. I consider this vector. I project it onto n. What am I going to get? I don't know, something bigger than b, right? So we know that this point is not on that hyperplane. Everybody on board? Yes?
Can you give the definition of the hyperplane?
The definition of the hyperplane. A hyperplane is an n-1 dimensional subspace inside of a n-dimensional space described by an equation of the form n some unit vector dot product with x equals some constant. Right? It's the set of points in an n-1 dimensional space such that all the points in there are perpendicular to n, or at least the dot product is some constant.
Can you write it down?
No. So I could write it down, but the important thing is the intuition, right? So I give you a vector. That vector encodes implicitly a set of all the other vectors in that space that are perpendicular to it. We know that that's going to be an n-1 dimensional space. Right? And all those points have the property that they're perpendicular to this guy. That's what a hyperplane is. Yes?
You can
p on the hyperplane and the normal vector n and fix the size of n. And what I understand is that the dot product between all those points p and n will be fixed for the hyperplane. But if you fix the magnitude of n, the magnitude of p changes for each p on the hyperplane. Isn't that true?
Yeah, so the magnitude of p is changing wildly. Way out here, it's really big. Out here, it's actually b. Out here, it gets really big again. But when we project that onto the unit vector n, all of the motion that we move in this direction doesn't add anything to that dot product because it's perpendicular to n hat. So that's kind of the cool thing. We're basically saying that I don't care where I am in directions perpendicular to n. The only thing I care about is how far has this point moved in the n hat direction. So any vector from here to anywhere on this hyperplane has moved the same distance in the n hat direction. Thumbs. Some of you aren't playing. All right, yeah, question in the back.
So I see that the hyperplane is perpendicular, but I thought for the two vectors to be perpendicular, the dot product had to be 0. So are we describing? I mean, if
I'm sorry, which scenario are you talking about here? So we've got n hat here.
right.
And what's the other vector you're imagining?
Well, I'm just looking at the equation that you wrote, n hat transpose x equals b.
Yes.
I'm just asking if n and x are vectors or.
Oh, great. So a great exercise whenever you're looking at an equation is to sort of drill yourself on what the dimensions of everything in it are. Right? If you can't answer that, then you probably didn't understand something. What are the dimensions of n hat? Let's suppose we're in an n-dimensional subspace. N by 1. X, n by 1 the way I've written it. And b? B is a scalar. Right? So n is a vector, x is a vector. Now, I'm not sure that answered your question.
So n and x are not perpendicular.
N and x are not necessarily perpendicular. Right? They could be, right? This could be x right here. And, actually, if we picked a vector, let's pick this point right here. Let's set x here. In this case, n hat, n transpose times x will be 0. Right? So the dot product can be 0. And if our equation has b equals 0, then this point is on the line. But if this distance here, the distance between the plane and the plane that goes through the origin, I don't know how to finish this sentence. Okay.
So that's a formula for the hyperplane, not for perpendicular vectors.
Correct. This is the equation for a hyperplane. Right. This is the property for n and x being perpendicular. N and x are perpendicular. If n and x are perpendicular, and that's the hyperplane you're talking about, then we know that the hyperplane goes through the origin. Right? If the right-hand side is 0, then that hyperplane actually goes through the origin. All right, and let's erase this so that nobody else gets confused. Okay. Any questions on that before we move on to something a little different? Okay, so we talked about hyperplanes, and one of the questions that I tricked Michael with, who's a very good sport about all of this, is how do we write the equation for a line? Right? We know that in higher dimensions than 2, the equation for the way that we specify a line is not with something of this form. So what's one way for me to communicate to you a line in 3 space? Right, I give you 2 vectors, and I implicitly say the intersection of the hyperplanes implied by these 2 vectors. In general, that's going to be a line. So one way to describe a line in n space is with n minus 1 vectors. Right? Because each of these vectors implies a hyperplane. And the intersection of n minus 1 hyperplanes is going to leave a one-dimensional subspace when we're done. And we know that any subspace that's one-dimensional, we can call a line. Right, we could actually go even farther and say one way to describe a point, still in n space, would be for me to hand you how many vectors? N vectors. Right? Because with each one, I lose 1 degree of freedom. And so by the time I've lost all n degrees of freedom, I'm down to a 0-dimensional point. OK, so we can look at this, and that's great. But there's something kind of silly about it. Right? Isn't there a more compact way for me to describe a point than to give you n vectors, each one containing n numbers? Right, this is probably the worst possible way of encoding a point. Right, it takes n squared numbers to do it. So what would you rather do? Here are the coordinates of the point, right? So what I could do, so this is the hyperplane way of doing it. What I could also do is I could say, here's your point, P naught. Right, P naught is a vector. It has n components. It tells me where the point is. Right? Similarly, a line is kind of silly. Right? So what would be a way of, right, so we hear 2 points. We know we're going to need 2n numbers. Can someone tell me, how might you provide a generating function that generates all possible points on a line? I like it. So let's say P naught plus lambda v1. So in this case, P naught is just some point. You can think about this as sort of an offset where this point, the line goes through this point. And then v1 is the direction that the line travels in. Right? So you give me some scalar, and I'm moving up and down the line in some direction. Let's do a quick image. Here's a line. Let's say P naught was right here. Actually, P naught could be any point on the line at all. And let's suppose v1 was this, right? Because v1 points in the direction that the line travels. For various values of lambda, I'm moving up and down the line. All right, could I do this for a plane? Well, in this case, I shouldn't say plane. I told myself I wasn't going to say the word plane because what the heck does a plane mean? So can I do this for a 2-dimensional subspace? Yeah. So for a 2-dimensional subspace, one thing I could do is I could give you n minus 2 vectors. Right, so I'm making a table here. I don't know if that's clear. It's nicely sorted, don't you think? Yeah. Lambda 1 v1 plus lambda 2 v2. Right, so there are really 2 ways of describing a space. Right, I can describe a subspace in terms of carving dimensions out, handing you hyperplane after hyperplane that reduces the dimensionality of the subspace. Or I could build up the subspace by giving you sort of a recipe for manufacturing points that live in that subspace. Does that make sense? There are 2 different ways of thinking about the problem. Now, those of you who have taken a linear algebra class, can any of you tell me a word for these spaces here? What's that? It's a null space, right? If I hand you a set of, let's call them simultaneous vectors or simultaneous equations, and there's some wiggle room left at the end, that space is called the null space. Right, we'll talk more about this later, but basically, if I hand you a pile of vectors and you intersect all the resulting hyperplanes, and you end up with some space left over, maybe it's 0-dimensional, maybe it's 5-dimensional, the dimensionality of that space is the null space of that matrix. Oh, I said matrix. I haven't said matrix yet. So it's a rich tapestry where some of the sewing needles make a round trip before others. That makes no sense at all. All right, so more on that next time. OK, so let's try a little checkpoint, another checkpoint. Here is a set of 3 simultaneous vectors, each one giving rise to a hyperplane. And what I want you to do is to tell me the dimensionality of the null space. I hope that's dominoes. All right, so x equals 12. So what I've written here equals minus 106. What I've written down here are 3 hyperplane equations for a 3-dimensional space. Right? What I want you to do is to tell me what is the dimensionality of the null space. And be careful. It's a trick question. It's a tricky question. One. Who said 1? Why is that?
Looks like one of them is a combination of the other.
They are. Right? So I said for the most part, we're going to ignore this degenerate case where 2 hyperplanes might be linear combinations of each other. Right? For example, if I give you 1 hyperplane, I've got an n-1 dimensional subspace. And if I intersect that with the same darn hyperplane again, I've still got an n-1 dimensional subspace. Right? In order for hyperplanes to keep reducing the dimensionality of the subspace, they have to be linearly independent. What we find in this case, what's your name? Kevin. All right, what Kevin has pointed out is that these are not linearly independent. Can you guys tell me how to, maybe a set of bases that I can compute these from? Oh, I said that badly. Let's just walk through it. So let's consider the hyperplane 1, 2, 3, and the hyperplane 1, 1, 1. Right, so how can I create this one? Or this one? That's one of these plus one of these. How can I create this one? Right, it's one of these and 6 of these. And of course, I can create this one with 1 of these and 0 of these. Right, so what we found is that I can generate all 3 of these hyperplanes by scaling and adding together 2 different hyperplanes. And so what that means is that when I start intersecting them, I'm not going to end up with a 0-dimensional space. I'm only going to end up with a 1-dimensional space. What's going on the right side? The right-hand side has absolutely nothing to do with what the size of the null space is. Right? It's just there to distract you. Right? The only thing that matters is what the directions of those planes are. Right? I can slide those planes around. If I got this plane and I got this plane, I can slide them around. It doesn't change whether they're going to intersect somewhere or not. Right? The right-hand side determines where they'll intersect if they intersect. But the only way for me to change whether they intersect or not is to start messing with their direction. And the orientation of the plane is determined by the normal vector, which are these guys. Everybody on board? Thumbs.
Can you clarify the relationship between the null space and the hyperplane? Because I learned the null space is from the linear system theories, and we learned the null space when we are teach about the mapping, linear mapping.
Mm-hmm.
That there is a range space and a null space.
Yep.
So I cannot see the relationship between these two.
So we're gonna talk more about that in just later today. So hold the question for just a minute, and hopefully we'll answer it in a bit. If we don't, ask me again. Okay, so I've basically already wrote a matrix on here, right? Most of you probably would have been perfectly happy if I had just done this, right? Right. Welcome to matrices, right? There's really nothing magical about matrices. They're just groupings of vectors. Now, those vectors can be interpreted in different ways. For example, in this particular case, I've got a matrix that can be interpreted as a set of simultaneous hyperplanes. I shouldn't say I'm saying simultaneous hyperplanes because it's like simultaneous equations. Let's call them intersecting hyperplanes. I could interpret them in a bunch of other ways, right? So I could interpret a matrix as a way of projecting from one coordinate system into another coordinate system. We'll talk a little bit more about that. So let's before we get too carried away with all the cool things that matrices can do for us, let's review some basic operations and definitions just so we don't get hopelessly confused. Let's suppose this is a matrix, and it's got m what? M rows and n columns. What I would call this an m by n or an n by m. I'd call it an m by n. All right, so quick check. If I say I've got a 10 by 4 matrix, am I talking about a tall and skinny matrix or a short and fat matrix? Tall and skinny. All right, just making sure, right? Because eventually you got to just be very comfortable. And it sounds like you all are. One problem-solving strategy, especially for 568, if you've got some nasty linear algebra equation, maybe it's a Shor complement or the Kalman update for state estimation, you're going to end up with these large linear equations, right, involving lots of matrices and inverses and blah, 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 blah. What's the easiest way to do sort of a check to make sure that it's sane? Check the dimensions of everything. Right? You'll catch probably 2/3 of all the algebraic mistakes you might make if you just make sure that all the matrices are the right sizes in relationship to each other. The big giveaway one is when we're multiplying matrices. Well, if we're adding matrices, what do we know about the dimensions? Right, I have to add an m by n matrix to an m by n matrix. If I'm multiplying matrices, what do I have to have about the, what has to be true of the dimensions? Right, the inner dimensions have to be the same. So if I'm multiplying an m by n matrix by some other matrix, I know that this dimension has to be the same as this one. This one has to be n. What about this dimension? Anything at all, right? Let's call it p. And what's my product going to look like? M by p. All right, and so for those of us who are a little rusty on matrix multiplication, I will sometimes, when I'm trying to build intuition, you're trying to track columns. I get my left finger doing the left to right thing and my right finger doing the up and down thing. It's kind of like this, except easier, right? So what am I doing? I'm doing these sorts of things. Wow, now I'm having trouble, right? Right? What do I mean when I say I'm doing this? Let's suppose I do this. What operation am I computing? A dot product, right? So a funny thing, dot products really do arise everywhere. If you're writing a linear algebra package, which is great fun, by the way, you'll spend a huge amount of your time optimizing dot products, because almost every operation you do can be written in terms of large numbers of dot products. Matrix multiplication, matrix inverses, Cholesky decompositions, everything. So dot products. All right, and if I do the dot product of the first row of this guy and the first column of this guy, what do I end up with? This element right here. Right, and likewise, if I do this guy and this guy, I compute the dot product, right? I'm computing the value of the element right about here, right? The ith row and the jth column of this matrix, right? So the product of this matrix here, which is the product of these two matrices, is basically the dot product of every possible combination of those vectors. That's actually kind of cool, right? What is that saying? Think about it from the sense of projecting points around, right? I'm really trying to see how all the vectors in one row, in all the columns of all of these vectors, what do they have in common with the rows of these vectors? Right? How much do they point in the same direction? Right? And there's a lot of combinations of them, so I've got a lot of dot products to compute. But I'd like you to start trying to think about this matrix multiplication, not as some mathematical turn the crank process, but in terms of geometric stuff going on. We're computing dot products, and those dot products have a geometric meaning. We're projecting these vectors onto these vectors, seeing how much they point in the same direction. I don't have a lot more to say about that today, but we will soon enough. Why do I keep scrambling my notes? It's really inconvenient. Okay, so we're going to return to the land of matrix vector products. So matrix vector products are a lot like matrix products, except that one of the matrices is really small. So matrix vector products are basically what's building into next week's lecture on AX equals B, right? Because there's a matrix vector product right at the heart of that. So let's consider this guy. This is a matrix. Let's call this a vector. There's a couple of ways to interpret this matrix vector product. So the first one is to consider this guy as some vector, right? It's a vector. And we've got some vectors here. Let me, in fact, erase this guy, V3. And now the product is what? V1 transpose X, V2 transpose X, V3 transpose X. Right, so what am I saying? I'm saying with a matrix vector product, I want to take this vector over here, and I want to test how much it points in the same direction as this guy, and this guy. It's like computing a correlation, right? An n-dimensional correlation. I want to see how much this guy has in common with this direction, and this direction. And that's going to be my answer. Let's see. The other interpretation I should also mention that we can interpret these as hyperplanes, right? So if I had AX equals some quantity, let's call it a B vector here, right? We're right back to what we just discussed for the last few minutes. We've got 3 hyperplanes, and I'm really talking about the intersection of those hyperplanes. Okay. There's another way to interpret this matrix vector product. We can consider what we call the column story. Maybe I should call these U's, because these U's are not the same as these V's up above. So this is what we call the row story. And the row story, in terms of a matrix vector product, we think about in terms of hyperplanes intersecting. This is the column story, which has something else going on. So what can we do to rewrite this guy in a way that makes a little more sense? Well, let's break up X a little bit. So let's call this X1, X2, X3. All right, so what am I going to have? I'm going to have X1 times U11. I'm going to have X2 times U21. And I'm going to have X3 times U31. And of course, I'm adding these guys together. All right, that's the first row. Ow.
Sorry, wouldn't it be U12 and U13?
This may be an unfortunate choice of notation. So this guy, when I multiply this guy, I mean the first element of each of these guys, right? So I'm still sweeping left to right here and up and down here. And so what I'm trying to say is that this is U11, this is U21. Right? I said it's bad notation because it's awkward. Let's do this instead. A, B, C. That's better. OK, so A1 x1 plus B1 x2 plus C1 x3. Everybody happy with that dot product? We can do the next row, right, which is going to be A2 x1 plus B2 x2 plus C2 x3. And no surprises here. The last row looks like this, B3 x2 plus C3 x3. And so what we can do is we can look at this a little bit more and say there's some structure going on here. Notice we got a bunch of x1s here, a bunch of x2s here, and a bunch of x3s here. In fact, I could rewrite this as a1, a2, a3 times x1 plus b1, b2, b3 times x2 plus c1, c2, c3 times x3. Right? It's a different way of writing the same product, but it's really looking at the problem in a different way. Rather than intersecting hyperplanes like we've been talking about earlier, now what we're doing is we're talking about a linear combination of the columns. So if I'm trying to solve a problem that looks like ax equals b, the game now is not to shift those hyperplanes to shift those hyperplanes around to find a point that intersects where I want them. It's to find ratios of the first column and second column and third column that give me the quantity that I want. So let's break this down a little bit. Let's hit both of these stories in turn. So we're going to start off back with the row story using a simple example. And then we're going to use the same example in the column story and show how, by thinking about the problem in a very different way, we still end up with the same answer. So let's consider the system. Where's my system? This guy here. 2 minus 1, 1, 1 times x equals 2, 4. So let's try the row story first. So what are we going to do? We're going to interpret this as a hyperplane, right, where the x could be any point that lies on that hyperplane. And here's another hyperplane, and we're going to consider the intersection of those guys. So let's draw those hyperplanes. All right, so how do I do that? Well, one way to do it, which is sort of the pretty geometric way, would be to say, hey, look, what is this row here? It's the normal vector, right? Whatever hyperplane I'm going to end up with, it's going to be perpendicular to this guy. Right? So here's my coordinate system. Here's x and y. If I consider the vector 1, 2, negative 1, right, there's my normal vector. And the hyperplane that I'm talking about is one of these that's perpendicular to it. Which one? How do I figure out how far away from the origin I need to go? Based on the right-hand side, right? It's 2. Although in this case, this isn't a unit vector, right? So the fact that this isn't a unit vector is going to mess with this a little bit. It's not 2 units in this direction because I'm actually amplifying my signals because this is not a unit vector. Right? So what is the magnitude of this guy? The length of this vector, if I multiply a vector by this, I'm basically increasing its length by the square root of 2 squared plus 1 squared. Right? So it's multiplying the length by square root of 5. And I know that the length I really want is 2. So how far should I go? 2 over the square root of 5. So I go 2 over the square root of 5 in this direction, and then draw my perpendicular, and there's my hyperplane. I did not draw that even close to scale. What is approximately 2 over square root of 5? It's a little less than 1, right? So my ticks are bad here. Let's make this 1 here and this here. OK, I just fixed up my scale. I drew the intercept in a very bad spot. Now we do the same thing for this guy. Right? And this, what do? I start off by considering this is the unit vector. This is the normal vector to the hyperplane. So I know that whatever plane I write out, it's going to be perpendicular to this guy. And I know that I need to be, that the intercept is going to be 4 over square root of 2. Everybody with me? Right? Square root of 1 plus 1. So that's 4 over the square root of 2. 4 divided by 1.4. It's like 2 and change, right? I don't know. So it's like somewhere here. And then this is going to be perpendicular. Right, so there's my other hyperplane. Now what am I doing? I've got sets of hyperplanes that I'm intersecting. So the solution that I'm looking for is where these two guys meet. And if I had actually drawn this to scale, we would have, if I'd drawn it properly, we would see that x equals 2, 2. Right? We can just verify that mechanically, right? 4 minus 2, 4 minus 2 is 2, 2 plus 2 is 4. Right? So if I'd drawn this exactly right, these two hyperplanes would have met at 2, 2. Everybody okay with that? It's sort of a practical example of what we've been talking about. Let's try the same problem with the column story. Yes?
For the row story, in the original kind of theoretical example that you wrote, is it V1 transpose or just V1? I'm just confused by that.
Here?
Yeah.
Uh,
I was confused with multiply two column vectors.
No, he's,
Right, yeah.
whenever you say vectors, it's always in a row, always in a column, right?
Right, so the issue here is that I drew them as row vectors. And so in this case, I don't need the transpose. You're right. Right, and we can check that from the dimensions if I'd been a little more careful. Because I clearly drew this as a 1 by 3. This is a 3 by 1. Right, and so the dot product, I don't want the transpose. I want to end up with a 1 by 3 times a 3 by 1. Thank you. OK, now to the column story. Now the game is a little different. I've got a store that contains all the 2 1s I can possibly eat, all the 2 1s I could possibly care to buy. And on the other shelf, there's a product with all the minus 1s and 1s, as many of them as I possibly want to buy. And the game is, how many of these should I buy such that when I add them all together and I add them to as many of these as I bought, I end up at 2, 4. Does that make sense? So we know the answer. Let's just see what it looks like. We know that, in fact, the solution is that x equals 2, 2. So what I know I'm going to need is 2 units of this and 2 units of this. So let's take our coordinate axes. 2 units of this is going to take me to 4, 2. Right, so here's my first leg of travel using 2 units of this. And now I want to travel in 2 units of this direction, which is going to be minus 2, 2. So I'm going to end up here. Everybody clear on what I did? And where did I end up? 2, 4, which is what I wanted over here. Right, so this is the other way of thinking about it. Right? We've got the row story, intersecting hyperplanes. Column story, going to a store and buying things so that you can mix them together. Right? Finding a linear combination of vectors that gets you somewhere you want to go. So I have sort of a fun example here. Let's suppose that you wanted to eat right. You go to the US, what government agency tells you what to eat? It's the FDA, right? All right, and so the FDA tells you something like, hey, fatty, you should really be eating 2,000 calories a day, 50 grams of protein, and 65 grams of fat. Right? And I look around, and I like going to Arby's, and they've got a chocolate milkshake, which has 119 calories in it for a very small one. 3 grams of protein and 3 grams of fat. So here's my chocolate shake. I also eat peanut butter in the morning. I put it on toast and stuff like that. So peanut butter has 165 calories, 7 grams of protein, and 14 calories. And then finally, let's suppose I'm a good boy and I just eat some dry cereal in the morning, which has 120 calories, 3 grams of protein, 1 gram of fat. So let's suppose these are the only 3 things that I can eat. Right? So the game here is to find out how many shakes I should eat, how much peanut butter I should eat, and how much cereal I should eat. Everybody on board? Right, that's the column story. We're mixing stuff together to arrive at our goal, US recommended daily allowance. And for those of you who have found this suddenly deeply engaging and personally relevant, I did actually compute the answer, and it starts off with a really happy fact. You should eat 25 milkshakes, 0 peanut butter, and -8 cereal. I'm not going to tell you the appropriate technique for that. All right, so you can imagine solving this. You could intersect the planes and do sort of the same thing before. One question I want to ask, sort of leading up to tomorrow's, solving this problem, coming up with these solutions, I didn't do this by hand, right? I used MATLAB for that. Solving problems would be a bit easier if Arby's sold fat packets, mayo, I guess, protein packets, beef, and what did I miss? Calorie packets, sugar water, that's Coke. Oh man, I've got an example. Right, why would that be easier? Because in each of those cases, I would basically have just one of these elements active at each one. Right? And so I could really trivially say, hey, you know, the Coca-Cola only provides calories. And so if there's a solution, it's got to be that I drink 2,000 calories worth of Coca-Cola. Right? Because none of the other ones provide calories, let's say. It's not true, but. So there's something about that we can do to save computation time down the road if we have this structure where things aren't mixed up so much like this. Right? If we have something that looks more diagonal, that's actually going to make solving the systems easier. And we'll see that in tomorrow's lecture. OK, we're not quite done yet, but we're getting there. So one of the other applications I talked about for matrix vector products, I mentioned we could think about them as simultaneous equations and things that we need to solve. We've got the row story, column story. The other one I mentioned is that a matrix can represent a change of coordinates, a change of variables. Right? So you can imagine that basically, can you believe I forgot I had stuff on here? All right, so what I'm going to do is I'm going to treat a matrix as a a black box. I'm going to have some matrix over here, and I'm going to put points on the input. Let's call these x's. And I'm going to get some points on the output. Now, in this case, I'm going to stick to square matrices, but in fact, this makes sense even for rectangular matrices. I'll let you think about that when you get home. But the idea is that A is going to transform my data into some other coordinate space. Let's try a simple example. Let's suppose that I hand you, I've got a robot with a sensor on it, and it's poking at some rock on Mars, and it says something like, this rock is red, it is 100 degrees Kelvin, and it weighs 30 grams. I just completely made this up, and I won't remember it in 30 seconds. But let's suppose that those aren't the units that we wanted. Right? One very simple application would be to change the units of the data that was fed into us. Right? For example, I could change the grams to ounces. How would I do that? So if I don't want to change the color, let's suppose color is encoded as a number, I just put a 1 in here. Let's suppose that I want to leave the temperature alone. But I want to change grams into kilograms. Right, what do? I put in a 0.001. Right, it's a very, very simple application of the idea of changing our coordinate system. In this case, it's just a simple scaling. How many of you are familiar with Fourier transforms? Right, so Fourier transforms are a change of coordinate system. So basically what I'm going to do is take my input data, which might be pixels in an image, and I'm going to multiply them by a matrix that's going to give me the frequency components of that image. Right? Both of these examples are pretty cool because A is actually invertible. Once I've done that, I can go back from kilograms back to grams, and I can go back from the Fourier coefficients back to the time-space images, the time-space stuff. So this is cool. I want to build some intuition. So A can be a black box, but what can we figure out about what the change of coordinates is by looking at A? Right, so what we want to do is build some intuition by looking at the matrix A and try to figure out what it's telling us about how we're changing the coordinate system. Does that make sense? That's our goal. All right, so let's take a hypothetical matrix A in 3 space. I actually have an example here for some reason. I don't know that these numbers make any difference at all, but why not? 6, 4, minus 1. And I multiply x, y, z over here. You give me any x, y, z over there, and I can give you some new x prime, y prime, z prime. And what we want to do is we want to understand something about what this spatial transformation means. Well, one thing that's a nice thing to do is let's try some easy points on the input, right? And see what happens to them. So what's a nice point to try on the right side? Yeah, I like 1, 0, 0, but 0, 0, 1's a good one. We'll do that one too. So what if I put in 1, 0, 0 over here? What am I going to get over here? 3 minus 2, 1. Anyone think that's kind of interesting? I just lost my marker. What happens if I put 0, 1, 0? Right, I end up with this column, 1 minus 2 minus 1. And if I put in 0, 0, 1, what's happening? I'm plucking out this guy. So what is this saying about looking at this matrix and understanding something about what's happening to my data? Well, I know that if my what was my x hat direction going in is going to end up being here. Right? So this is, where's my notes? Where does x hat go? Where does x hat go? Right, that's the first column of this matrix. Everybody see how that happens? How that works? Obviously, this is where y hat goes, and this is where z hat goes. All right, well, that's cool. Now, there's another way of looking at it. That's kind of a column story view of this. I'm sorry, that's a sort of a row story view of it. Well, no, it's a column story view because we're plucking out columns of this guy. Is there a row story to go along with this? Well, so what do we know about the row story? We know that the row story consists of doing all these dot products. We're going to take this vector, and we're going to compute the dot product with this. And what is that saying? We're projecting this point onto this guy. Then we're projecting this point onto this vector. And we're projecting this point onto this vector. It's almost like this is the vector that if I take some point and I compute the dot product with it, it tells me where the new x coordinate will be. I actually just read you the definition of what that dot product is. But this information here is telling us something about what direction the new x hat was, so that when I correlate it against my input point, I know what the projection of the right-hand point is going to be on the new x-axis. Does that make sense? So this is actually equivalent to where did x come from? Where did x hat come from? Right, so what do I mean by that? If I had 3, 1, 6, and let's suppose this was an orthonormal matrix, which this is not, then this would correlate exactly with this guy. And that would point, we would have already had a point pointing in the direction of the new x hat direction. You know what? Let's move to the example because it's going to make things a lot more clear. So there's a special case of transformation matrices which are rigid. So a rigid transformation matrix is one that preserves, any guesses? The scale, shape, angles between things. You know, a rigid body transformation basically treats a set of points as a rigid object. Right? I can do anything I want to this thing, right? But it's still pen-shaped. Whereas like the scale matrix that we talked about before might stretch things out. That's not rigid because the thing going in doesn't have the same shape and size and angles as the thing going into it. So one very classic type of rigid body transformation is a rotation matrix. I'm just rotating an object in space. So let's actually construct what the rotation matrix looks like for rotating in 3 space 90 degrees around the z-axis. So what we want to do is come up with what the A matrix looks like so that if I had a world full of points over here and I projected them, the points over here would look like I'd taken the whole world and rotated it 90 degrees around the z-axis. Everybody on board with what we want to do? Thumbs just for sanity? Great, great. So first thing to do is let's draw what we're trying to accomplish. So let's draw a nice right-handed coordinate system. Everybody remember right hand? So I start with my thumb, x, y, z. So I'm going to draw my coordinate system like this, x, y. And which way does z need to go? Yeah, towards you guys. All right, now I want to rotate the world around the z-axis 90 degrees. Which way does that mean? Does that mean this way or does it mean this way? Right, how do we know how to solve this? Right-hand rule again. You stick your thumb in the direction of the axis that you're rotating around. And then your fingers are curling in the direction that is the positive direction. Right? So I said, let's rotate around the positive z-axis. So I'm going to stick my thumb in the positive z-axis, and my fingers are pointing in the direction of positive rotation. So what I mean is I'm going to take the board and I'm going to rotate it this way. Right? Like this. Everybody on board? A little right-hand rule review. That's always fun. How many of you have been in a physics exam or something like that, and you see someone writing and they're like, oh boy. Okay, so let's try to figure out what we want here. Now, what do we know? This is the easiest one to figure out, the column story, in my mind. Right? Where does x hat go? So if I had x hat, which is the vector 1, 0, 0, where should x hat end up after rotating it 90 degrees? 0, 1, 0. Everybody happy with that? Where should y end up? So y was 0, 1, 0. Now it's going to be where? Right, it's going to be here, which is in the negative x hat direction. It's going to be minus 1, 0, 0. And what happens to z? Nothing, right? We didn't touch z. Very good. We just built a rotation matrix by inspection. Yeah?
Can you do y one more time?
Can I do y one more time? Sure. So the question that we're asking ourselves for this column here is, where does y hat go? Right? If I have y hat over here, where should it end up after rotating it by 90 degrees? So it was 0, 1, 0. And when I rotate this vector, imagine this point right here, and I rotate it 90 degrees, it's actually going to be in the negative x direction. And it's not going to have any y component anymore, and it's never had any z component, so minus 1, 0, 0. All right, let's take a look at this. We built the matrix. This is right. But we can look at this again from the perspective of the rows. So, like I said up here, these rows mean, where did x hat come from? Right, what do I mean? So after the rotation, I've got an x hat. What was x hat before I did the rotation? Where did x hat come from? Right, so after doing the rotation, I have a point that ends up here. Where was it before I did the rotation? It was here, right, which is 0, minus 1, 0. Whew. OK. I've screwed this example up before. It's easy to make mistakes in the strip above the whiteboard. All right, so second question we can ask is for this row. This is going to be, where did y hat come from? Right? So after doing the rotation, here's y hat. But what vector got transformed into y hat? The one that was minus 90 degrees this way, right? Which is 1, 0, 0. 1, 0, 0. And the last one is easy. Where did z hat come from? Well, z didn't change, so actually it was still just 0, 0, 1. I think that's awesome. Don't you? I'm only slightly kidding, actually. For years, I looked at rotation matrices as being confusing things and had absolutely no idea that I could just read off the columns to understand where the unit vectors went, and read off the columns to understand where the unit vectors came from. Yeah?
So you do x one more time.
X, this one?
Yeah.
Sure. So the question that we're asking here is, where did x hat come from? So before I did the rotation, there was some vector that after the rotation got mapped to the x hat vector. So given that I ended up here, where should I have started off in order to end up there? Right? Which would have been down here, so that I would have rotated up here. I guarantee you that you'll go home and, unless you've done this like a couple of years running, you're not going to remember this. It's absolutely worth going through it. But the main thing right now is to remember that there is meaning buried in these matrices. You can look at these matrices and understand a great deal about the system you're looking at. Right? I want you to stop thinking about matrices as numbers and start thinking about them as vectors that have geometrical significance. That's kind of the whole recurring theme of this talk. Is this helping at all? You guys?
Yes.
Great. OK, let's hit just a couple more types of rigid body transformations, and then we'll call it an evening. Actually, I didn't mean to say rigid. Other types of transformations. Let's suppose I've got some points over here, and what I want to do is I want to enlarge them all, right? So maybe what I've got is a 3D rendering environment, and what I want to do is make everything appear bigger. So how would I build a rigid body a transformation matrix that makes everything look bigger? Let's say 10, 10, 10. Right? Does that make sense? We're basically just going to pick out these components and just enlarge them all. We're not messing at all with rotating, because you can see everything's nice and diagonal. And there's no sort of cross-pollination between the x and y axes. It's just a straight scaling. OK. So we've done rotation. We've done scaling. What's the next one? Translation. All right, everybody. Let's suppose I want to move the whole world over 1 unit to the right, 1 unit in the x direction. What do I do for my matrix? Right, so I can't. Right? There's no, if this is x, y, z, there's no matrix that I can put here that when I multiply this guy will shift x to x plus 1. Right? There's no matrix where this is true. Right? That makes sense because I only have a multiplication to play with. Right? There's the amount that I would need to scale that would depend on x. So we've got a bit of a problem. Now, how many of you have done some sort of 3D rendering or computer vision? OK, a few of you. So there's a trick to getting around this. In fact, there's a whole geometry about it. But for today, we're just going to live with the trick, which is to introduce a homogeneous coordinate. So the idea of a homogeneous coordinate is to extend all of our vectors with an imaginary fourth component. I don't mean imaginary as in like square root of 1. I mean something that doesn't have a real physical intuition. So what I'm going to do, I'm just going to append a 1 to the bottom of this vector. Now, A, instead of being 3 by 3, is going to be 4 by 4. And over here, for now, let's assume that we're going to have a 1 at the bottom as well. Does this solve my problem? Can I do translation now? Right, because what I can do is I can position some scaling factors here that are going to act against the 1. Right? So I can get some constant shifting over it. So let's be specific. How exactly do I fill in this matrix? So let's just do the first row. The first row is going to have how many elements? 4, right? Because I've got 4 elements here. What are they? Right, 1, 0, 0, 1, because I said I wanted to shift this guy over by 1. Right, we can multiply this out. I'm going to have 1 times x plus 0 times y plus 0 times z plus 1 times 1. Right. More generally, I could put in some t sub x, and I'd end up with that. All right, where does y go if I want to translate in the y direction? Right, 0, 1, 0, there. And z, 0, 0, 1, tz. What do I do for the last column? 0, 0, 0, 1. Right, so like I said, if you get into image formation for like a perspective camera, you're going to be exposed to places where this bottom coordinate is not always 1. Basically, we can implement a perspective transformation by fiddling with this bottom component. But for the purposes of where we're going to stop for today, we just want to preserve a 1 here so that we could later translate this point again. Right? If we always leave a 1 back here, we're always retaining the ability to do some other translation down the road. Does that make sense? OK. That is all I've got for today. So for tomorrow, and by tomorrow I mean Monday, in here, we're going to be talking about AX equals B. So we're going to use a lot of the intuition. We're going to revisit the row and column story a little bit, but mostly we're going to talk about how to solve these linear systems. So we're going to hit LU decomposition, Cholesky decomposition, talk about how to handle rank deficient matrices. And as far as an application, we're going to look at regression, linear regression, and nonlinear regression. So I hope to see you all on Monday. Thank you.